Okay, we are going to discuss experiment 16, simple harmonic motion. It's the next experiment uh, that we're going to perform. And this, I always try to scroll it on here. It's got to be scrolled on my iPad. Now, whenever we do an experiment, you want to, if you need to print something out to fill it by hand, or if you're doing it electronically, you want to do the TI portion. Those are the ones that we're doing. You don't have to do the CI. You can forget those. Those are computer assisted uh, experiments. We don't have to do it. Now, having said that, if you want to answer the advanced study assignment CI questions, you're welcome to, and I'll even give you some extra points for doing it, because one of them you may not be able to answer because um, some of them you may not be able to answer because of the way they're applied to the computer um, uh, procedure. Anyway, so you want to turn in the advanced study assignment, and I want you to read the overview, introduction, and the objectives. And basically, what we're studying is this here, Hooke's law. The force equals minus kx, and we've discussed this in the lecture notes. Force equals kx. Now, what is kk? The constant is called the spring constant or force constant, and it's a relative indication of the stiffness of the spring. And when the particle or object in motion under the influence of a linear restoring force, such as that described by Hooke's law, undergoes what is known as simple harmonic motion, and hence the title of the experiment, simple harmonic motion. I think sometimes in the lecture notes I abbreviated SHM, but we'll continue on. Now, the here again, it's highlighted. The spring constant is called the stiffness constant, and the greater the K is, the greater the stiffness. And the you need to, in your version, in your printout, unless they have since corrected it, but I'm not sure which version this is. Check and see that this bottom on page 229 or this general form, it should be y equals mx plus b. They missed the m, so that make that correction. Let's see. Let's okay. Here's an important point. The argument of the cosine term, cosine 2 pi t over the period is in radians rather than degrees for this equation here they're talking about. Okay, but this equation that I've got highlighted here, that's the one that we're going to concentrate on. This is going to give us our spring constant. We're going to solve for K. We're going to solve this equation TI 16.3 for K. Now, if I don't really know which edition I'm using here, but your 8th edition may have, it may even be a different experiment number, but the important thing is the name simple harmonic motion. I think in other versions, it's called Hooke's law, I think, or a name something like that. Okay, so the first thing we're gonna do, we're gonna skip this rubber band elongation. So this, we're not doing A, so we're gonna skip that rubber band. I don't have a simulation for it, and I don't have a set of weights, so we're gonna skip that. We're gonna go on to the spring elongation. Now we're doing a virtual experiment, so we're going to suspend a mass on a spring, and we're gonna measure the distance displaced for more and more mass. And if we plot mg versus y, well, we should be able to come up with a spring constant. You get a slope of a line, you'll come up with a spring constant. So that's the straightforward one. You just add some weight. That's a force. Force is equal to minus kx. If you solve for, if you plot force over the displacement, you should get the k. All right. The next thing we're going to do is we're going to cause it to oscillate. We're going to cause the spring to oscillate, and using a laboratory timer, I'm right in this section here, using a laboratory timer or stopwatch, release the spring weight hanger from the predetermined initial displacement and determine the time it takes for the mass to make a number of cycles, of complete cycles. I'm going to use 10. And then you're going to plot the graph of the average period. I'm in this paragraph now. Plot a graph of the average period squared versus the mass, and draw a straight line that best fits the data point. Determine the slope of the line and compute the spring constant, K. Now, I probably covered it up a little bit. Let's erase this. K is equal to 2 pi squared over the slope. So you're going to plot t squared over m, and you're going to come up with some, oops, didn't mean to do that. You're going to come up with some line. You're going to come up with a slope, and then you're going to put that slope in here. And k will equal 2 pi squared, quantity squared, so basically it's 4 pi squared when you get finished with it, divided by the slope. And I've already pre-populated it. That's it for the introduction. In the next video, I'll actually do the this portion of the portion B, the spring elongation.